So I just want to flip through a few things to show you some of the kind of in a straightforward way, how I ask and answer questions. One of the questions that I alluded to is that we don't know how much water there is to use in a basin always. So we know kind of how much is flowing out of the river, but we don't know how much is there that could be used by others. So this is really tells that story. This basically asks the question, how much water is in any drainage basin? How much is available? And so I've got a cartoon here that shows the land surface in green, and underneath it, the bedrock surface, which in most parts of the state of Indiana anyway, is not also an aquifer. It's usually pretty much impermeable. So you've got the land surface, and then you have soils before you hit bedrock. And if you go up a stream, if you start at the bottom and go up a stream, the stream flow gets lower and lower as you go up the stream. You'll also see there's a reservoir in this. That's the blue blob. That's a reservoir up one of the drainages. And so that's my cartoon aquifer. And so what's important to think about and remember is that any stream that is flowing all of the year, so it's perennial, that stream is in direct hydraulic connection to the aquifer that's in its neighborhood, that's next to it or below it. So the aquifer actually is bleeding into the stream and supplying the stream with water when it hasn't rained for a month. So the reason there's still a river there when it hasn't rained for a month or two is because the aquifers are leaking into that stream. And that's kind of a key part of thinking about what the relationship is between the aquifer and the stream flow that's runoff. So I want to move this. Is this bar on top? Can I move it somewhere? Yeah.
Yeah, but we can't see it on our side, just FYI.
Okay. So without any withdrawals, the stream flow up river at A is less than the stream flow at B. And it's kind of obvious. Maybe people don't think about it, or they do, but stream flows increase as you go downhill, as you go downstream. And that's because more and more of the watershed that is this shape that I'm showing, the watershed that's draining into this area is flowing into the stream. So the stream flow is proportional to the amount of land surface that's flowing into it. And the way I think about this and the way I describe it is that the flow in the stream is fast water. It's water that fell on the ground, ran off through the soils into a ditch, and then flowed downstream. It's gone in a week or so. It's out of the system. It happened. But the groundwater that was recharged slowly and fractionally, not that much water, goes into the aquifer, and then it seeps out over decades in this area. So it takes a longer time for groundwater to leave the watershed than it does surface water. So in the spring, in any of these cases, you'll see more surface water runoff because of the storms that happen in the spring. And in the fall, stream flow is really supported by discharge from the aquifers. So if you were to go out into the watershed that I've drawn here, this cartoon land, and you were to sample the water in that river, that blue line, the chemistry of the water during the springtime would be very different than the chemistry of the water in the fall, even if the flows look to be about the same. And it's because it's made of different ingredients, basically. There's high dissolved minerals in the water in the fall and lower dissolved minerals in the stream in the spring. So at the end, though, it's a mix. The stream flow at the bottom of what I've shown is that it's a mix of both the old high TDS water, the total dissolved solid water, and it has also a bunch of low total dissolved solid runoff from last week's storm. So you've got a mix of water. You think it's like, oh, this is good White River water. Well, actually, it's some water from long, long ago and some water from yesterday. So it's not one age. So you also have to think about the fact that in the watershed, in most parts of central part of the state of Indiana anyway, where we have enough topographic relief for reservoirs, we have them. We've dammed up streams that feed the river. So we can do this. This is old school engineering to dam up a river and store water behind that dam so that you can release it during the low flow periods. And that water is definitely adds to the water budget in this basin. But you can do more than that. You can also do kind of the opposite. You can put a diversion in the river and you can divert water out of the river so that you can apply it to any use, whether it's cooling water for a power plant or whether it's manufacturing of something. And that water is subtracted from this, especially if it's used and consumed and evaporated. And there's another way to take water out of the system. So you can intercept the water that's flowing in the stream. That's one way, but you can also intercept water that was going to go into the stream, but now it's being pumped out by a well. So if you have a well in this watershed or any watershed, you're intercepting water that would have gone into the river. So you're subtracting from the flow, but the timing is not the same as if you just directly divert it right out of the river. There's a lag in when that shows up in the river, that subtraction that you're taking water out. So when you take a lot of water out of the aquifer, you can do another thing. You can change the discharge in the stream by pumping the aquifer, by subtracting water that would have gone into the stream but no longer is able to because you're catching it on its way there. And that aquifer withdrawal is really a part of the water budget for this watershed. And then if you put big well fields together, you can intercept flow that would have gone into the stream and reduce stream flow, but you can also pump the water so hard that you can pull water out of the river into the aquifer, kind of flipping the sign of the relationship between the aquifer and the river. You can turn the aquifer into a recipient of water from the stream instead of a provider of water to the stream. And that's actually on purpose. A lot of people do that on purpose, and there's good reasons actually for that, for water management reasons. And so a lot of people stop there about all the negative parts, the subtracting, pumping, the diversions. But the other thing that we do is, because we have the Clean Water Act, by the way, and that's a federal law, we have to discharge, and that discharge is regulated from wastewater treatment plants, from irrigation return flows, from all the different regulated discharges we have. We measure those and we actually know their concentrations of certain compounds, or they're limited in that way. But we have a lot of information about what other water is being added to the flow from other dischargers. So in Indiana, it has resources that are limited during seasonal and long-term droughts. So just to clarify and make this obvious, when the demand for water is highest, stream flow is lowest. So July, August, September is when we use the most water. And it just isn't coincidence that that's also when there is the least water to use. So while, and there's also some geography that's important, that if you go further and further upstream, there's less water to begin with in the system. There isn't that much of that's drained into anything. When you go further downstream, there's more water. So effectively, this says the Mississippi River is a good place to go for water because it's way downstream of most things. And when you go very far upstream, like on the West Fork of the White River, which is a tributary to the White River, which is a tributary to the Wabash River, which is a tributary to the Ohio River, which is a tributary to the Mississippi River, we're way upstream. We're like 4 layers of upstream, and it's a huge watershed. But when you go further up, it even is lower. So we have USGS stream gauges. We can look at the stream flows in different basins and see differences between basins that are really illustrative of how they react. So if we measure stream flow at the end of this cartoon watershed, what are we measuring? So this illustration is a cartoon of what stream flow is made up of. And what it shows is that stream flow is made up of the surface water runoff. That's just exactly what it sounds like. Runoff that over the land surface. There's some shallow flow that goes in, and it's called interflow. There's also water moves into the soil and then exits as groundwater into the stream. So you've got runoff happening, you've got infiltration happening. And there's another thing that's occurring is that some of the water that is going onto the landscape is actually being used during the growing season by trees and plants, and they can take almost all the water and keep any recharge from happening during the summer. So in Indiana, recharge happens mostly during the non-growing season, not during the growing season, even though it rains really hard. So a lot of the water that seeps into the ground is used. Some of it gets past the root zone during certain times of the year and goes into groundwater. So stream flow is, it's a funny long equation here, but it's really just a bunch of things that I just explained. The surface water flow, Q is flow of surface water, is made up of runoff, is made up of groundwater discharge, is made up of the discharge back into the river from regulated drains, from also pump, minus the pumping that occurred in the basin, minus the diversion that occurred, minus the drain, or plus the drain discharge and any reservoir discharge. So this is a fairly, the reason it's worth talking about is there's a lot of parts. And each of these parts usually goes with an activity of some kind, an industry. And why it's worth even going through the effort of making this cartoon is that it's important for people to realize that it's not just drinking water companies or utilities that are involved. It's a bunch of people, a bunch of engineering, a bunch of industry, a bunch of communities, farming, everything. And we're trying to protect the water for all of those uses. So there's an engineering, the equation I've just arranged, so there's like a natural side. The surface water is both runoff and groundwater discharge. Like if nothing was happening on in this watershed, that's all that there would be. But because there are people, there are these other pieces of the puzzle. There's an engineering sort of side that we can change if we want to. If we look at a hydrograph. That's what this picture is. The red line shows how much the rate of flow is at a stream gauge. It shows these spikes that happen right after it rains. And it shows those spikes going really high up because that's the total flow that's measured at that location. But the blue part underneath, where the blue line is, that's the discharge from groundwater that's going into that stream. So there's runoff and there's groundwater, and there are methods for separating those two out in a hydrograph. And it's a real cool thing. I spent a lot of my time trying to figure this out when I was in graduate school, trying to figure out can we see the groundwater piece, and because I wanted to figure out how much was infiltrating, and you can do this to answer that question. And a stream hydrograph is its signature. These are pretty funky looking hydrographs, but it's because they are the entire record for the Wabash River at Lafayette and the Kankakee River near Davis, Indiana. They've been measured since the 20s. And there's some important information in here that's fun to look at, in my opinion. And that is, you can see how much they vary, but also what's important to point out is that the y-axis here, the discharge, the up and down part of this, is really pretty small on the Kankakee River compared to what it is on the Wabash River. If you just look at the order of magnitude, so the high flows are 10 to the 5th, so a lot of zeros at the top end of the Wabash River, and the bottom end is in below 10 to the 3rd. So there's more than 100 times difference between the high flow and the low flow. And the Kankakee River, if you look at it, it's a half of an order of magnitude, so 5 times. 5 times, and one is 100 times. That's stunning. I mean, to think they're both kind of big rivers. They have slightly different areas and dimensions, but still, that's a little amazing that you can have a river like the Kankakee flowing at 5x or 1x, whatever the number is, and the Wabash will go up to 100 times its flow and high in a single year. Why is that? And that's the signature of the river is part of the answer. So these are both 80 years. Okay, 7x and 70x. Those two lines are those. So tenfold difference between flood and drought. And so the reason is that the Kankakee River is basically a sandbox. The basin itself is left over from when glaciers were melting rapidly and spewing out huge flows of water that carried sand, and that sand dropped out before the fine sediments did. And the Wabash River is further down into the middle of the state, and it was really there's a lot of clay soils, and so when it rains on the Wabash River watershed, not a lot of water goes into the aquifer. A lot of it runs off. So the image on the right is a high runoff, fast, flashy streams. Floods are a problem. And the one on the left, the Kankakee River, it's really hard to get that river to flood. It used to be a marsh. It's kind of extra flat, extra sandy. So rivers have different signatures based on their properties. And one more recent illustration of this is if you look at 2012, which is kind of a flash drought here in the state, one of the things you'll see is that the Kankakee had their drought, but it was like a couple days, basically. It went below its normal drought flows, and the low flows on the Wabash River lasted for a longer time. It's not as interesting, I think, as the hydrograph, but at least it points out some of that same thing. Same response, a slow response for the Kankakee to change, and a fast, flashy response for the Wabash River. Less runoff and more base flow in the Kankakee. So water supply is limited by infrastructure. That's what I talked about earlier, the engineered piece, because that's the amount that we can divert. Water availability, which is to me the resource, is more defined by the resource and the environmental limits that we put on how much we can take from the system. This shows how large in our state the Wabash River watershed is. The green on the left-hand image, and it's made up of sub-watersheds that are illustrated on the right-hand image. But it's kind of amazing because our state is almost a John Wesley Powell state. That John Wesley Powell said that state boundaries should be coinciding with watersheds to manage the resource. Our state, again, I think coincidentally, matches almost the Wabash River watershed. Some Wabash, there's a little Wabash comes out of Illinois in the south, but it's pretty impressive that we've captured almost the whole river. And I illustrate this just to show that each of these colors that I show these larger rivers in are what their flows are on their lowest flow every other year. So every other year, this is a statistic that's commonly mentioned when you're talking about stream flows, is the 7Q2, which is simply the flow, the average flow over 7 days, that's the 7, that you can count on happening every 2 years. The lowest weekly flow. So it's kind of like your seasonal expected number. And the blue is the higher flow, the bright blue, which is more than 500 million gallons a day past those gauges. And then it goes up to the red is 10 to 50 million gallons a day. And the reason that this is kind of interesting to look at is it shows what I was describing earlier. As you go upstream, the flows decline fairly rapidly. And you can see that happening in the middle of the state where the economy is booming is really where each of the rivers ends. So we have a definite interest in managing the resources that we have in the state. Yeah, for those, just to make the point even more clear, there are some counties in the state that have perennial problems, and these are those counties. Basically, if it's near the word dry, there are counties that have problems with delivering water to residents. Every county, we developed a template to show how that county uses water, how much they use, whether they use groundwater or surface water. And every county can be kind of mapped onto a priority level in terms of whether they have to worry about water management. Hamilton County is north of Indianapolis, and a lot of the new development and the communities that are growing fast are using the aquifer there. So this simply illustrates that and shows that most of the water use is for public supply. And it also just shows where the streams are in relative location to where the wells are. And the wells are the circles and the streams are the lines in this case. This is a different location, a different story with a lot of water use from different users. So the green dots are the irrigation. This is Shelby County, I think, or Johnson County. So the question really is, what's changing? Why is this important now? And the problem that we're facing now is growing metro areas. So demographics are really not what they were 20 or 30 years ago. More people are being added to cities than are being added to rural communities. And that concentration has consequences for water supply and discharge of water. So we have more users in central locations pumping more water. And in this particular state, planning is not systematic, and nor is it regional. So we don't have a method. And I'm trying to actually create that method. So the recent project we did in central Indiana for the Finance Authority, Indiana Finance Authority, is to address this problem by starting with this one region. Water quality can limit your options because water supply can be limited not just by there's no water in the river, but the water in the river isn't drinkable, or the water in the aquifer isn't drinkable. So water quality can force our hand. In our state, new reservoirs are not an option. It's just rare that anyone would propose it now. You want to go through this or no? What do you think?
I think that this will be great for a lot of the debate teams that are in the state.
Okay.
And so I'm learning a heck of a lot.
Okay. Okay, good. That's all I wanted to hear. I've got another one.
This is great.
Okay. So where are we using water in the state and for what purpose? That's a question I think is a really interesting question, because it's not, I had no idea, honestly, when I asked this question. So this map helps you see what the use of water is for, total. So if you look in the middle of the state, where there's a dark blue Marion County in the middle, that shows that it uses the blue color of each of the counties is how much water they consume, they use from the based on the DNR's Significant Water Withdrawal Facilities Database, SWWF database. And what it shows is that in the areas along the big rivers, we use a lot of water because we have power plants. That's the red in the pie charts. So every one of these pie charts shows who uses which fraction of the water, which of the sectors uses that water. So we have industry, big steel up in the Great Lakes, on the shore of the Great Lakes, and we have power plants along the Wabash and the Ohio rivers. And then if you go into the Kankakee Basin, which is just south of the Great Lakes, and you stretch across to the northeastern corner, it's dominated by green, which is agricultural irrigation. And that's where a huge fraction of the irrigation water use in the state occurs, is in that sandy soil, that where water is a limiting factor on corn production. So this year, I don't know if you knew this, but this year corn prices are through the roof. They're higher than they were in the early part of the last decade, which they were topping out then. So there's no penalty usually in that environment to overwatering. And all of the farmers added these wells not because they thought they needed the water, but because the bank wouldn't lend them the money to plant unless they had irrigation wells. And so with the irrigation wells that they now have to have, and with no penalty of any kind for overwatering, because the sandy soils will drain out, everybody will irrigate very much to try to save their crops. So what this means is that there is latent capacity, unused. They're basically wells that aren't pumping, that are sitting out in the landscape, that can be all turned on when needed. Okay, and that's what agriculture does. It turns on a bunch of wells that changes the conditions in that state or in that county. You have counties in that middle northern area have falling populations and have rising water use. That's not true in hardly any part of the country. So it's to me, it's interesting and it's common. It's like that is to me a region that should be, that group of people, the farmers need to talk about what are we doing and how many more can we add? Is this safe, or is there any consequence in water quality? Are streams drying up or are they not? How are we affecting the neighboring community, the town that's also pumping from that aquifer?
And so it all seems like it's driven from a bank assumption that if there's a drought that would ruin the crop. So they had a micro level analysis of each farm being independent, but not a macro level analysis of it being a part of a whole system.
Right.
Wow.
And that's common because banks make decisions based on an individual or their corporation, whatever, that they present their credentials, and the bank says, sure, we'll loan you that money for that new property, their parcel that you want to buy. Your neighbor's going out of business and you want their land, but you better you need a well on it. And then because it lowers risk. Risk is the guiding force in finance. So it was really impressive to me that this was not as much a farming issue as it is a banking issue. Okay, so there's a way to even think about this completely differently. There might be weather insurance mechanisms that could be developed at a federal level, even, or a state level. You could come up with new ways to provide that reduced risk without this consequence. Or alternately, you get everyone in the room and you say, do we know what we're doing? And let's see how we're pumping. Let's look at a wet year. Let's look at a dry year. Let's look at a high price corn year and a low price corn year and try to figure out whether we can manage this differently. In the center of the state, around Indianapolis, it's mostly light blue colors. The light blue color is public water supply. And the darker the county, as I mentioned before, the more is the larger the pie is, let's say, the pie chart pie. So you've got some kind of entirely drinking water systems all around the middle of the state. The middle of the state is the economic engine of the state as well. It's where growth is happening. It's where the economy is centered. 2.5 million people live there. So it's it's critical. So there are different methods. Only 3 years ago did the utilities in central Indiana begin talking to each other about water. And they formed what they call the Regional Collaborative. It's a low barrier to entry group of people that talk about water planning informally. They don't write things down too much. They talk about what they're doing and what they think they need in the future. So they're having the beginning parts of the conversation, and it's really been great. It allows for collaboration, which is really key. Along the two southern borders of the state, the one that's along the Ohio River, and then the one along the Wabash River on the eastern southern side, you have these big red dots, and those red dots are coal-fired power plants. And coal-fired power plants are being decommissioned or are being switched to fuels that use less water. So in most of those, the water that will be used in the future will be much less, or they will be gone. So the power plants in much of the southern part of the state are going to be shifting over. So that will no longer be once through cooling and heating up the water in the river, it'll be less water taken out of the river, which is a good thing. So this is a kind of a thing that's going to happen and will improve our condition in general.
So is that also true about the plants that are on the west side here?
Yeah, yes, excuse me, the west side as well. I probably said the east, but the west side, most of those plants are located along the big river so that they can have access to the river itself. I guess there's another interesting tidbit here, and that is the tan brown color. It's sprinkled to the between the green and the central Indiana blue. You see those brown up there? Mm-hmm. All of those are industrial, self-supplied industrial users, most of whom are producing parts for automotive applications. So that's tied to Michigan, more or less, or the automobile industry. So it's kind of an interesting, like, again, blur your eyes and look at it, and you can see that a lot of those uses are that industry, and that industry is sort of fading, but maybe coming back. And batteries and electric vehicles and all of that, we don't know. And we are a manufacturing state. And I think this is another interesting fact, is that in the middle of 2014 or 15, research was done to try to identify which state had the most water users that depended on abundant water supply. And that state is Indiana, of all of them across the country. Michigan did the work because they thought they were going to be first, and it turned out to be Indiana.
Wow.
So we need water for our economy in a way that most don't. If we look at just 1 year's use, 2013, and we just look at who used the water, and you size the dots according to their dimension, power plants use the most water. They don't consume it, but they need it for their production. They throw heat into it and they put it out into the river again. Public water supply is relatively small. Industry uses a lot as well. If we instead look at who uses groundwater, which is a piece of the total, so we're no longer looking at who takes water out of the river, but we're looking at the aquifers only, public water supplies become the big dominant player across the state. This is everybody in the state. This is all together. And ag is sort of like surprisingly big, at least. It's like, wow, I did not know that, that ag was that big. But let me just do another thing. Let's not look at the groundwater only. Let's look at just the summertime in groundwater. So who's using the water during the summertime? This is statewide across our state. Agriculture in 2013 almost used the same amount as all public supplies across the state. And this is about 5,000 wells total for the agricultural wells, I think. So it's a lot of wells, all pumping a lot of water, but all during 3 months. So the problem isn't the amount they use over the year, it's the amount they use during the driest time of the year, when other people want it and need it. So they're actually competing directly with the public water supplies at sometimes in some places. So this kind of points out a thing that other people have thought about but never really quantified, is how much of an effect could this be? If we look at the whole year, so our state has a very impressive record of water use. We split it out by public supply, agriculture, industry, energy and mining, and then at the top is the total. If we look at all of those, and we look at the groundwater side, which is on the right, all of them except one are trending up. And that continues to today. And one of them is going down, but that's really understandable. It's industrial uses because industries are leaving the state and the country. And so it's really interesting to look at. And there's another thing that I think, this is the East-West story, that might be useful, is that if you only look at the industrial manufacturing in our country, and you wonder why we use so much water for business, for industry, this is why. So if you look at the orange regions, red, brown, whatever, that's where we have the most industrial concentration of manufacturing. And if you look at the blue regions, it's the least industrial land uses or industry. So if you see these maps and you look at Indiana, you say, wow, it's as brown as any. It looks pretty brown. It's what I said before. It depends on that. But it also goes with the USGS's map of the United States that shows Indiana is this bright blue, dark blue in the all industrial water uses. So Louisiana is higher. We surpassed Louisiana last year. In this is higher, but in last year we are above Louisiana. If we look at power generation, people don't look at this either. They look at power and they say, oh, they must have as much power production out west. No, they don't. They don't have it at all. Look at our side of the country is where all the power is produced, because that's where the plants were built in the 70s and 80s. So we have coal-fired power plants all over. And if we look out west, we don't see as much in the way of power plants. And by the way, same thing, if you look at where power generation water use is occurring, it maps pretty directly between this image and this image, which is the kind of the data from the USGS. And it kind of maps to population density, but not quite. If you look at irrigation water use, the Western states dominate. They're drier, they need water to grow anything there. So even though Arizona doesn't seem like a place to grow cotton, they grow cotton in the deserts near Phoenix. And Indiana doesn't use that much. It's historically not used a lot of water for irrigation. But when you look at the change in irrigation, who is using more than they used to and who is using less than they used to, the western side of the country is using less and less each year. Big amounts of change. Water rights are important. The value of water is important. The cities are buying it from the farmers. In our part of the country, it's gone up more than 2 times, maybe even as much as, many tens of percent. So it's really important to not just think about the relative amounts, but where is it changing in which direction? So if you look at this map, this is kind of where farming is potentially conflicting with other demands, urban demands. And it shows conflict in the red, where there is high farmland quality and high development activity. So all around the middle of our state, we have this balancing act that we're doing between the value of the land for for agriculture and the value that it has to communities for home. So there are lots of different fights that are going on along the way. So in some parts of the country, you've got stream flow depletion and the limits on it, the laws and rules are limited by how that stream flow depletion affects trout streams. That's Michigan. Michigan has a water withdrawal assessment tool, they call it WWAT, that is the thing they use to see whether additional pumping will cause an impact to the streams. And if it does, you can't pump more water out of it. So Michigan has come up with a rule and a plan so that you can say, I want to put a well here, it'll pump 200 gallons a minute during these months in this aquifer, is that okay? Then they'll come back, the model will actually answer the question for you and say, you can't do that. You'll have to put it in a different place or a different aquifer, or no, it might be the answer. Wisconsin has come up with different methods, but they've had problems with their court. They've not been able to kind of agree on a method, whether they can count all the users, not just the new users of water.